Yes, let us now talk about the fundamental framework of quantum mechanics. So this starts with the concept of the wave function. We learned from de Broglie's hypothesis that a moving particle is associated with matter waves, and these matter waves are the waves or the wave packet formed by the superposition of two or more sine waves which are abstract in nature, which are not physical, they are abstract waves, and the superposition of these waves produces the matter waves. Now we want to define one function that is called the wave function. What is this wave function? A wave function is a quantity whose variations produces the matter waves. So that is what the wave function is. Now what is this wave function like? Is it a positive function or a negative function, a real function or complex function? We see that in general the wave function psi is taken to be a complex function. So like we can take the wave function psi as equal to a complex number a plus ib. Now if I take the conjugate of that is psi star, it is equal to a minus ib. This is also a complex number. Now how does a complex number represent something physical phenomena, right? So for this, let us see now the product of the psi and psi star, that is called as mod psi square. So when you do the product of these two, we get it equal to a square plus b square. Now you see this is something very real and positive value, right? So now you see that therefore mod psi square is real and positive, and therefore it must be having something to do with the physical phenomenon. We actually see that the probability density or the probability of finding the particle per unit volume at a given time is proportional to the mod psi square value at that time. So this is how we see the physically the value is obtained using the mod psi square. But we see here that the mod psi square value may exceed 1. It may come in something like 2.5 or 10 like that. But we see that the probability value always lies between 0 and 1. So this is a problem here. So its probability density is therefore only taken to be proportional to mod psi square. We don't get the exact value of probability density using the mod psi square. To overcome this problem, we have to do what is called as the normalization of the wave function psi. So when you do the normalization of the wave function psi, we will be able to get the exact value of the probability density. So how do you do the normalization? Let us consider some region where the particle is present, and over that region if I take the integral of mod psi square dv, then find out how much it is. Whatever value we get, let us call it as n square. Now the normalized wave function is obtained as psi n. The new wave function psi n is equal to psi divided by n. Psi is the original wave function divided by the value n. And what is this value n? So n is obtained from this here, n square. Taking the square root of this integral here, we get n, and we have to divide the original wave function psi by n, and we get the normalized wave function psi n. Now this wave function psi n is ready to give us all the information related to the system exactly, not the proportional values. Therefore now we see that if I take the integral of mod psi n square dv, it's equal to 1. So this process is called as the normalization. So here we see that therefore now we get mod psi n square is equal to probability density. It is not proportional, it is exactly equal to the probability density once we do the normalization. So here wave function psi is like a database which is able to give all the information related to the system, but that wave function may not be normalized or calibrated. We have to normalize it, then we get the normalized wave function, and we will be able to get all the exact details related to the system from that normalized wave function. Now let us see what are the properties the wave function must satisfy. Can any function be taken as a wave function, or should there be some properties the wave function should satisfy? we see here that the wave function psi must be a single valued function. So that means for a given point x, it must give a single value. So if it is not single valued, what would happen? If it is not single valued, then the probability of finding the particle will also be not single valued. It will be different 2 or more values, but that is not meaningful. Therefore we see that the wave function psi must always be single valued function. Again, another property the wave function must have is the wave function must be finite at every point. Again, same thing here. If it is not finite, then the probability of finding the particle would become infinite. Again, that is not true. Then the psi function, the wave function psi must be a continuous one. If it is not continuous, then you won't be able to get the derivative of the function which is required in the differential equation for the wave function. So therefore the wave function psi must be continuous function. So we also see that another property is psi dash. The first derivative of wave function must be also continuous. This is again because we have to go for the second derivative of the wave function in the differential equation. Therefore the first derivative must also be a continuous function. Then we see finally that the wave function psi must be normalizable. It must be normalized, and you should be able to get the exact value of the probability density from the wave function. Therefore the given function must be normalizable. So these are the properties the wave function must satisfy. So this is how the quantum mechanics runs. So for a given physical system, there will be a wave function psi associated, and that wave function psi is able to give all the information related to the given system, but that wave function may not be calibrated. Therefore we have to do the normalization of that wave function using the normalization procedure, and after the normalization is done, we will be able to get the exact value of the probability density about the given system. So we have to also see that the given wave function satisfies the different properties there.